Walaikum
Assalam.
So I'm putting a schematic of a forward system, which is made of forward feed MED system, which is made up of 4 effects. And actually, I just put it here so that you would have like a comprehensive look at the flash boxes as well as the preheaters, look at the flow rates that are in and out on each one of them. So that if we need to analyze, for example, flash box number or associated with effect number 3, then we would know what are the flow rates in and out of that unit. So that's why I brought this one in here so that it would have been easy when we have a system like that to do the mass balance as well as the energy balance for each one of the components. Keeping in mind that, for example, when we are considering, let's look at flash box again associated with effect number 3. We have basically what is coming here is D1 and D2 together. So these ones are coming from the previous effect. But we are going to add this one to them, which is basically D2 or capital D2, which is the vapor that has left effect number 2 and it has entered here, and it will condense and then join them as they are getting in. However, part of it is going to leave, which is D-3. It will go up where it will condense in the preheater, and then it will come back again. So it's a flow out and in, the same flow rate, so it did not change. But the small D3 that has entered here is going to condense and join it. That's why when we look at the leaving content here, it has D1 plus D2 plus small D3. So the small D3 is the small quantity that has left the effect number 3, condensed in the preheaters, and then is added to the flash box. So that's just to have a look at this and see it. Okay, and then it will cancel out after that, because the one which is coming after this is going to be at the end. It should be D1, D2, D3, D4. Let's see if it's complete. Please have a look at it. I'll just leave you for about a few minutes to have a look at it and tell me, is there something missing here in this figure or not? Let's think about it together. I think there is something here. I'm just leaving it for you to find out.
The vapor those are leaving effect number 4, D4, entering into the condenser, but where they are going?
I mean, the vapor that leaves to the condenser, you mean this stream?
Yes, yes.
Condenses in the condenser, and then here it is, it joins as liquid product. It is joining the D1 plus D2 plus D3, so that here we have D1, D2, D3, and D4.
Oh, yes, it is correct.
Actually, there is something here in this figure that should have been added just to clarify the issue here. Let's look at, or should I leave it to you for a while to have a look at before I discuss it with you? Maybe I can wait for a couple of minutes too.
What is happening in the flash box number 4?
Actually, yeah, that's a good point. I mean, this is something that could be missing, that from flash box number 4, we should have like D-4 should go up and then go down, but there's no flash box, there's no preheater associated with it. That's why we can take this whole thing out and it will not affect us.
Exactly.
which means that we don't need flash box number 4 here, since the vapor that, or maybe what we can do, we can say that there is vapor which is going to leave here and it's going to join D4 and enter to the condenser. And then it will be collected later. You getting my point?
Yes, yes.
Okay, so that's something probably I can do as sort of a repair for this figure, is to take a stream of flashed off vapor that is going to leave flash box number 4 and it's going to join D4. It will condense in the condenser, and then here, actually what is going to leave will be D1 plus D2 plus D3 minus D-4. And then there's D-4 coming in here so that they cancel each other. This is a good point. This is one of them. The second actually is related to whatever I'm writing here. I mean, this, what is leaving here, this green arrow is D2. But we have taken a part of it, which is small d2 to the preheater, isn't it? Which means that whatever is going to condense here is not going to be capital D2, but it will be capital D2 minus small d2, which has gone to the preheater. And then this D2 that has gone to the preheater is going to join the flow which is going to the flash box back again. So whatever is going back to the flash box should be D2 plus D-2. D2 is vapor that has formed here, we are taking it to condense, and D-2 is the amount of vapor that has flashed in the flash box. Both of them are going to enter here as vapors. They will condense, and then small d2 and d-2 are going to enter or to go back to the flash box as liquid. That's why here you can see it as d1 plus small d2. And whatever should be coming here, capital D2 minus small d2. So the d2, small d2 would cancel out. I hope this point is clear. And again, the same point is repeated in the vapor, which is leaving the third effect. So that's the thing I just wanted to discuss with you related to this. And I would suggest that if you are going to analyze a system like this, do something similar to that, like draw all the connecting lines between the different components of the system and reach the corresponding value of flow rates on top of it. If you got the flow rates correct, then the energy balance is going to be correct as well. Any questions? So we could identify a couple of points where corrections can be done to this figure. Now I'm going here, maybe I can, I can sketch another one because I need to do like a freehand sketch for the next point that we're going to consider. So here we have, suppose that we have a unit which is made up of 4 effects. Effect number 1, effect number 2, effect number 3, effect number 4, and then the condenser at the end. And we have seawater coming in, and then the seawater is leaving. Suppose that we're talking about a forward feed system. So this is going to be sprayed here, and then whatever is going to leave from here, it will be the feed for the next effect. And so on. So whatever is leaving the second effect will be the feed for the third effect. I'm just now handling the seawater. And then whatever is leaving the last effect is going to be rejected to the sea. Meanwhile, if we are going to talk about steam, for example, then steam coming from a power plant it's better maybe to change the color. So, and the vapor leaving this effect is going to enter to the next effect for condensation. I'm taking the simple case where there's no flash boxes. The vapor leaving this effect is going to enter to the next effect. And the same thing is applied here. And the vapor which is leaving here is going to enter to the condenser. Will it condense and then it is going to be collected as product. So this is the product line here. And whatever is coming here is m dot feed plus m dot cooling water. M dot cooling water is going to be thrown away and m dot feed is going to be retained. So here we have m dot cooling water thrown away, and whatever we're getting is basically m dot feed. And after that, we're going to have this one as D1, this is as D2, this is as D3, and here we have D4. And this basically is B1, this is B2, B3, and this is B4, which is m dot rejected brine. And maybe what I did not do, it's because this is seawater, it's been spraying here. Now, the vapor which is leaving the last effect, what we may do is that we connect an ejector here. This ejector is receiving a motive steam at a certain motive steam pressure. This ejector, what does it do? It entrains some of the vapor here, which is m dot entrained vapor. It is going to add with the m dot motive steam, and then we are going to get m dot motive steam plus m dot entrained vapor. This is what is going to be used as a source of heat. We have entrained some vapor here to compensate for it. We are going to get back the entrained vapor to join our product line. And the motive steam is going to go back again to the power plant. So that instead of taking all the steam coming here to the unit is coming from the power plant, which is m dot s, now we have replaced it by a smaller quantity coming from the power plant, and the rest is generated from our system. So when we are talking about the performance ratio of this unit, then basically it's going to be m dot distillate divided by steam coming from the outer source, which is m dot motive steam. And then the equations which are related to the performance of the TVC, the thermovapor compressor, can be used as we did it for the single effect evaporation. So we still have the compression ratio, which is basically PS over P entrained vapor. We have entrainment ratio, m dot motive over m dot entrained vapor, and RA is obtained through a correlation that is a function of the motive pressure, steam pressure, and entrained vapor pressure in addition to temperatures. And we have the pressure and temperature correction factors. So this is something that you have seen before. The only thing here, the only difference is that it is associated with a multi-effect desalination system. In reality, the TVC is not that small, but actually it may, you may find it in some cases extended over almost the length of your system. So it's quite lengthy, a big part or a huge part of, or a huge component of the desalination system. When we are going to do the analysis for such a system, it will be the same thing as we did in the MED case, except when we do the energy balance for the first effect, then we can write it a little bit differently. So if I'm going to say here that I mean first effect, then I can write that Q for the first effect is m dot motive plus m dot entrained vapor. Both of these are multiplied by HFG S. So this is the condition S. That's the stream of steam which is coming in, which is made up of these two components, m dot motive and m dot CV. And we know that they are related in entrained vapor. And we know that they are both related by RA. So if I know the value of RA, then I can determine the two components. This is also is equal to the m dot feed CP T1 minus T feed plus D1 HF G1. By the way, I have prepared the new homework. I'm not sure if I put it on Blackboard or not. Do you remember finding it on Blackboard, or I should upload it? Actually, that's the homework that should take care of the single and multiple effect evaporation system. Maybe I did not, because I remember last night I was still working on it, preparing it. And when I finished it, maybe I closed the computer right away. I did not upload it.
No,
so
doctor, it's not there. It's not there.
Oh, so I'll upload it, inshallah. Fine. So that's the balance for the first effect. Previously, when we used to do the multi-effect evaporation without TVC, we used to say that this is m dot S into HFGS, and m dot S was totally coming from a power plant. Now it's not. It's basically partially from the power plant or the boiler, and the rest is for what is vapor that has been formed within the system that we have. And then the rest is going to be the same. And we know to obtain the value of m dot m and m dot EV, then we have this expression of RA. So normally for this kind of problems, there are ways to calculate m dot F, ways to calculate D1. So this right-hand side of the equation is known. Then the only unknown becomes this component, m dot m plus m dot entrained vapor. We have another equation that identifies the relation between m dot motive and m dot entrained vapor, where RA is obtained through an empirical formula. So we have two equations and two unknowns, and you can calculate m dot motive and m dot entrained vapor. So that's the only kind of difference that we can see in the analysis of a multi-effect distillation system with thermal vapor compression. The thermal vapor compression is not necessarily associated with forward feed. But we can have this system of TVC also applied with a parallel feed. So that's something that we can do. We can have a parallel feed and the same thing can be done. And in this case, this thing will not be there. But anyway, I mean, you know the difference between the parallel and the forward feed. So what I meant is that the TVC is not necessarily linked to a forward feed MED system, but it can be done with a forward feed, with a backward feed, with a parallel feed, with a parallel cross feed. All of these are possible utilization of this. The remainder of the analysis is the same. So the only difference is that we are having this kind of additional balance equations for the TVC or the thermovapor compressor. Now let's look at another work that we have done. I was talking to you about last time that in some cases or in some studies that we have done earlier, we said that why this necessarily is associated with the last effect. Why don't we take the whole thing and shift it forward? And instead of extracting the vapor from here, why don't we extract it from here? Or from here? Or from here? Why necessarily the fourth effect or the last effect? Typically, we are talking about an 8-effect system in the industry. So we found out upon doing the analysis that the best situation or the best case is to put your ejector to receive entrained vapor at the middle of the TVC. So if you are talking about 8-effect system, maybe effect number 4 or 5. If it's a 12-effect system, it's maybe number 6 or 7. So this is basically, we are basically finding out that the performance, the PR, performance ratio, is higher. The mass flow rate of the cooling water is less if you are putting your TVC in the middle of the MED system, not at the end. And we have done some sort of a detailed analysis for that. Maybe I can share with you a part of it now. But this is basically the kind of difference or the addition that we are going to consider now or consider today for this system compared to what we had earlier. You can now anticipate that if I want to talk about the multiple effect distillation system or desalination system, and instead of talking about a TVC, I would talk about a mechanical vapor compressor. Then it's not something new. I mean, you can handle that. If I take out this condenser and actually take the vapor which is leaving the last effect, and this vapor can get into a mechanical compressor, and the compressed vapor is going to come here. So that makes an MED system with mechanical vapor compression. We might not be talking about the mechanical vapor compression today, but just to show you that it would be the same. And this mechanical vapor compressor needs some power input here to operate it. So the energy balance is going to be estimated in terms of the specific power consumption for this case. And in that case as well, we are not going to have condensers, but instead of the condensers, we are going to have a couple of heat exchangers. One of the heat exchangers is going to handle the distillate, and the other one is going to handle the brine. So the brine is leaving at relatively high temperature before we can make use of that, so that the seawater which is coming from the sea, will part of it pass here, and the rest is going to pass here, and basically they'll be combined together to provide the feed. So it can be a parallel feed, or it can be a forward feed. So we are doing preheating for the seawater in these two heat exchangers. One of them is by the hot brine, and the other one is by the hot product, and then you can have your performance this way. And in this case also, we're not going to have something which is going to the power plant. But basically, the quantity that we have condensed here, basically this is D4. So this is basically D4, and it will join D1 and D2 and D3. So what we have here basically is D1 plus D2 plus D3 plus D4, or this is our M dot distillate. This is for the mechanical vapor compression. We'll be talking about that next time. Maybe we can put it in a way that I would have it in a sort of a group work, that I'll give you a figure like that. This figure is empty, just have that the kind of effects and the heat exchangers in, and then ask you to put the mass flow rates in, so that you would be able to figure it out. Okay, so this is as far as a schematic of a multi-effect desalination system with thermal vapor compression or with mechanical vapor compression. Now let's have a look at the presentation that I meant for such a system. So I would, it's a PowerPoint. Let me just open the file. Again, what I'm going to show you is some sort of a detailed presentation that has something that is not very much related. You will just see what I mean now. So I need to share this. What I'm going to share with you is a part of the master thesis presentation of Khaled Abdelbasit, who was doing his master, maybe it was back in 2016. And the work that he has done is looking for multi-effect desalination technology with vapor compression. And specifically, we're focusing on that issue of the TVC. Where shall we put the TVC so that we can have sort of best performance of the system? So his presentation starts with the outlines, followed by talking about the water problem, that more than 97% of the whole water in the world is in a salty form in the oceans, and only a very small fraction is available as sweet water in rivers, for example, or so. And this is, it's not evenly distributed throughout the world. And that's why there is an issue, or there's a crisis of water shortage, sweet water shortage, or potable water shortage all over the world. And then talking about the quantity of water is constant, but the population keeps on increasing. It might exceed 9 billion in 2050. And accordingly, the share of everyone in terms of availability of sweet water decreases. And this should be compensated by building more and more desalination units so that they can convert more of the salty water into sweet water. The desalination process in general is a separation process. You need to separate the salt from the water so that the water becomes, let's say, healthy to drink. And there are different technologies related to solar, to desalination systems in general, either units that are operating based on heat, or based on work, mechanical work, or based on electric or voltage difference, as you can see it here in the electrodialysis system. And the thermal desalination systems are the ones that are they mimic or they imitate the natural water cycle. So evaporation from the oceans, clouds would form, clouds will go to less temperature areas, they are going to condense into rain, and the rain, as it falls down, it's going to be again going back again to the ocean through flowing through the porous media, which is the sand, and then it will go back again to the ocean. So it's some sort of a complete cycle for the water. This is a general classification of the desalination technologies based on the type of energy that is going to be added. Electric energy, we have the electrodialysis. Thermal energy, we have MED, MSF, HDH, solar stills, and even freezing desalination is taking the energy out. So it's again a thermal system. And then the mechanical systems are basically units operating with mechanical vapor compression or RO or forward osmosis. These are all mechanical operated units. Or the classification can be done based on membrane-based or thermal-based, and you find that there are so many branches for the thermal-based desalination. Actually, we can say that we have covered many of them so far, except for the last one that we have not yet talked about, which is the MSF, multi-stage flash desalination system. This is a single effect operation system, and that's something that we have been working with and analyzed this system already. Then the classification would get into the, what we have here is essentially, this is, what kind of a desalination system is that? Who can tell? Is it forward, backward, or parallel?
Forward.
It's a forward, yes, because basically all the fluid which is being preheated in the condenser is going, all of it to go to the first effect, it will be sprayed, and whatever will not evaporate is going to be sprayed in the second effect, and it is be repeated again. So it's a forward feed system. And here we have again the forward feed system on the top, the backward feed system here in the middle, and the parallel system, which is one that is below here. And it's a parallel system. There's no parallel cross in this figure. It's just a parallel system. This is just quickly some of the works that have been done. Probably some of these you've been exposed before, talking about the work of Al-Dasuqi in 1998. Al-Dasuqi, by the way, he's the one who shared authoring the book, which is there in the blackboard. He and Hisham Al-Touni, both of them. Al-Dasuqi died last year, alayhi rahmatullah. He was maybe 71, 72 years of age. And then in 1998, they introduced a mathematical model describing the MED system and gave a conclusion that PR is the major factor that, or basically here in this work, they said that it's independent of the top brine temperature, which means that the PR or the top brine temperature, increasing it or decreasing it does not really change the PR of the system, but the most influential part is the number of effects. And then in year 2000, they made performance evaluation of both parallel and parallel cross systems and looked if they are able to operate at high temperature, that would result in a smaller heat transfer area. Ali and Al-Fiqhi again looked at the forward feed system and said again that the PR is not relying on the steam temperature, but it is more dependent on the number of effects. Ophir and Lokiak, again, they said that if we compare MED and MSF, then MED is going to be better thermodynamically because of the lower energy requirement compared with MSF. Darwish, he's actually the one that most of them have learned from him, have done some work here showing that the MED system has advantage of operating at lower temperature, and that provides us a way that we can operate it with low source energy or low grade energy. The heat transfer rate is depending on the temperature difference across the effects. And he said again, in comparison between the MED and the MSF, then MED is basically consuming about half of the energy needed for the MSF. Then Darwish and Abdul Rahim developed an MED model, analyzed different arrangements, parallel, forward, backward, and so on. And for each one of them, they found that the number of effects is the most powerful parameter that controls the value of the performance ratio. Karen Mystery and others that was basically our work in 2013, talking about the advantage of cogeneration in being able to produce water and electricity. Darwish came back again in 2014 and he made a different analysis for the ejector or the thermovapor compressor compared to what we have done. Maybe in an opportunity, I can show you the work that he has done, because what he did is that he obtained an expression for the entrainment ratio, RA, which is different from the one that I showed you. It's just basically, he came up with a polynomial, which is, I can say it's a little bit easier to deal with. The objectives was basically to look at or to answer the question, what will be if the conditions or what will be the performance if we change the location of the thermovapor compressor in the system. So that was the question that we raised in 2014, 2015, and the work of Khalid here is the answer to that question that was raised. This is a typical forward feed system. It's a normal one, no TVCs, nothing at all. It just has its preheaters and flash boxes. And when you see here the flash box at the last one, it has done the thing that was missing in the previous figure. You see here, because the flashed off vapor that's going to leave here is going to join DN, or the vapor formed in the last effect, and both of them are going to enter to the condenser to condense. So that was actually, this line was missing in the figure that we started with today. And he was showing the results or the equations that are needed for analyzing the forward feed model, so that an energy balance for the model. LVI, basically he's using L here as a representation of HFG. In the engineering unit system, they are using L, or the metric system, they use L rather than HFG. So that's why it's written here. So steam which is coming from the power plant into its latent heat is used to sensibly heat the feed and evaporate part of it. Then the effect balance, or the energy balance for the rest of the effects, is going to be that DI HFGI, or LVI, is equal to DI minus 1 into HFGI minus 1. So, and this remains for the rest of the effects. The energy balance for the condenser, on the other hand, it is receiving the vapor which is leaving the last effect, multiplied by its latent heat of condensation, is going to preheat the feed, which is m dot cooling water, plus m dot feed from T cooling water to TF. So m dot Cp delta T. And then when we are looking at the brine, actually the brine, which is formed in the first effect here, is the feed, m dot feed minus D1, that's the brine. The brine will be sprayed here. So B2 is going to equal to B1 minus D2, and so on. So again, for the brine balance, you are going to have that brine B1 is m dot feed minus D1, and the balance of the concentration can follow. So m dot feed, x feed is B1, x1, and this is what you see here. Heat transfer area, again, we are looking at the heat transfer rate in the first effect that we have calculated earlier, this one. M dot steam into HFG of steam has resulted in, number one, preheating the feed to the saturation temperature and then evaporating the feed. And this is being expressed here in the expression which is being used for calculating the area. So D1 LV1, the latent part, the sensible part m dot feed, Cp T1 minus Tf, all of that is equal to A1 U1 delta T1. So A1 is equal to that expression that you see here. This is how we can determine the area of the first effect. If we are assuming constant area, then if you are talking about 8 effects, then the area of the 8 effects are going to be 8 times A1. The performance parameters for these units are given in terms of the performance ratio, m dot distillate over m dot of steam, and the specific flow rate of the cooling water. It's m dot cooling water divided by m dot, m dot cooling water divided by m dot distillate, yes. Khalid built his own model, and to make sure that model is correct, we compared the results that he obtained from his model with the results obtained by Al-Dasuqi in the book or in the paper, and this is what we could get at the end for given values of TS, TN, cooling water temperature, feed temperature, a number of effects. We could find that the deviation between the calculated values for our model and for a Dasuqi model that he reported, they are very close to each other. So here the maximum percentage difference is about 0.5. That means that the model is correct and we can start modifying it to what we need to do. These are some typical results of MED system. There's nothing unique about this MED. When you see this unit, you'll find that the PR basically is a function of the number of effects. This is N number 4, N number 8, N number 12. But the TS has insignificant effect. Actually, it decreases slightly with the TS, but that decrease is unnoticeable. And then the cooling water, again, we have less cooling water for the large number of effects, and the highest cooling water is for the low number of effects. The reason for that simply is how much vapor is going to condense in the condenser. In the case of 12 effects, the performance is almost, or the productivity is almost divided by 12. So less than 1/12 of the feed is going to go to the condenser. So it needs less water. But if you have 4 effects, then the flow rate is divided by 4. So higher flow rate, that would require higher quantity of mass flow rate for condensing that vapor. That's why larger number of effects are going to have higher performance ratio and lower mass flow rate of the cooling water. Then we turn to the thing that we discussed today in our class that we started with, or basically it was the second item, talking about adding a TVC into our unit. Whatever is coming here is m dot feed plus m dot cooling water, and m dot cooling water is going to be returned back again to the water, and m dot feed is going to remain with us. So here is it. It is going to receive some energy here. It will leave also as m dot, but at a higher temperature. It will receive energy here, and then it is going to be sprayed at effect number 1. So basically, this is a forward feed MED system. The steam here, which is reaching the first effect, is a combination of m dot motive and m dot entrained vapor. So this combination, m dot motive plus m dot entrained vapor, sometimes you like to call them m dot yeah, that's the condenser. So we're going to get m dot entrained vapor, and m dot motive is going to go back again to the power plant. Then the vapor which is leaving the state will be D1. Vapor is formed here to preheat the feed, which is coming here. And when you are looking at the quantity which is leaving here, this is basically D2, this is D3, and this is D4, out of which part is being taken up, which is m dot entrained vapor, and the rest m dot condenser is going to the condenser. whatever we did to fill this flow rates that are coming in and out of the preheaters, in and out of the flash box, that's something that you can do, I'm sure, based on what we have done today as we started. Where is the TVC located here? It is located to the last effect. So it is receiving part of the entrained vapor, which is formed in the last effect. This is the balance equations for the TVC. This equation have been proposed by a scientist. His name is Power. Publishing this work in 1994. It remained with use in the open literature for quite a bit of time until in 2014 came Darwish, and then he came up with a different way to calculate the TVC. Anyway, this is the one that we have been using always. I can show you or can share the other methodology with you a little bit later. So RA, or the entrainment ratio, which is defined as m dot distillate divided by m dot motive, is equal to a constant PS to the power divided by P entrained vapor to a power, PM to a power divided by entrained vapor, and then multiplied by pressure correction factor and temperature correction factors, where the pressure correction factor is given as a function of motive steam pressure. The temperature correction factor is given as a function of the entrained vapor temperature. Again, this work has been done, which means that equations have been built for that model. They are brought all together into the engineering equation solver, and we could come up with a prediction of the performance of this unit, as you can see it here, in terms of mass flow rate of the cooling water, surface area, specific heat transfer area, performance ratio, compression ratio, and RA, which is the ratio between m dot motive steam divided by m dot entrained vapor. So that's the entrainment ratio. And you can see here the maximum deviation is 1.3%, which means that the estimation is acceptable paradigm. Look at this figure. You'll find that the straight lines, the solid straight lines, are the ones that we have developed earlier for the multi-effect desalination unit. Remember, I can just get back a little bit to show you that this is basically the thing here. PR is going to be given as some sort of still a very, very insignificantly decreasing PR with temperature, which is TS. But when it comes to the adding the TVC, the performance is going to change, as you can see it here. So for lower temperature, the value of the PR for the TVC is significantly higher. So there is a way here that we can increase the performance ratio, which means that I can imagine a case like this where a thermovapor, an MED system which is being operated, and then we have introduced a TVC system into it. What you see here, you see that the performance is better of the TVC compared with the system without TVC. And this is obvious because when you are talking about PR, then basically you are talking about the ratio between m dot distillate over m dot entrained vapor. So whenever the entrained vapor value decreases, then the PR increases. And this is what we rely on whenever we are operating a system like this with thermal vapor compression. This effect diminishes as the temperature increases. But for the range of temperatures of operation of the TVC, where basically the top prime temperature about 65, so we're talking about a steam in the order of 80 degrees centigrade or so. For this range, there is a significant improvement in the performance of MED systems. the forward feed system also have been analyzed for the mass flow rate of the cooling water. Remember, in the last effect, we are taking part of the vapor to be entrained in the TVC. Accordingly, the remainder will go to the condenser. So the amount of water that will go to the condenser is going to be less. And that's why the specific mass flow rate of the cooling water is less. Again, specific mass flow rate of the cooling water is m dot of the cooling water divided by m dot distillate. We cannot help. Sorry, it's the yes. Here, because of the TVC is going to entrain some of the vapor. Then the quantity, this is, for example, dN. So this is going to be dN minus m dot entrained vapor going to go to condense in the condenser. So we need a smaller size condenser. That's number one. And number two, it would require less flow rate of the cooling water, which is going to result in saving in terms of the size of the condenser, that's capital cost, size of the pump, this is capital cost, and the running cost of operating the pumps for a smaller flow rate. All of this running and fixed cost reduction. The second question that I was telling you about was, what's the best location for the TVC? If we are talking about a system like that of 4 effects, should we put it here, or here, or here, or here? So we did the analysis in a way that the vapor can be entrained from this effect, or this, or this, or that one. So that choice was left to see. But we're looking for the case where we're going to have better performance of the unit. So which location is going to result in the best operation for the unit here? The results are shown here. Look at the PR. For the range of, now this, the solid line, the heavy line here, the bolded line, is the line where the TVC is located after effect number 2. The rest are the TVC is located at effect number 1, number 2, number 3. The range of operation of the MED is at a temperature of 65 to 70, which means that for the steam, it's going to be 75 to 80. So we're talking about this range in general. In that range, the highest PR is for the condition where the TVC is located in the middle. And you will see, interestingly, that this configuration, this figure here is qualitatively the same of whatever the number of effects and whatever the technology that we are using. I mean, is it parallel feed, forward feed, backward feed, whatever. They are going to result in the same, qualitatively the same thing, which means that if you are talking about 2 effects, you better your TVC, put your TVC after effect number 2 in the middle of the system. The benefits that we are going to get are, number 1, higher performance ratio. Number 2, lower mass flow rate needed for the cooling water. The bold line here at the bottom, which means that we are getting less quantity of seawater needed to condense all the vapor. And this is obvious because the quantity of vapor which is going to the condenser is less. So you need less water to make sure it condenses. Heat transfer area did not change. I'm talking about the overall heat transfer area. It was not really affected by the location of the TVC. Now, this is for the unit analysis. What if we need to do like a second law analysis? For the second law analysis, we need to look at what are the entropies in and out. So m dot exit into S exit is equal to m dot inlet into S inlet plus entropy generation plus Q over T. If the system was well insulated, then the Q over T is 0. So we're basically talking about the entropy generation for each one of the components. So after doing the analysis for each component, the energy analysis, we just write the second law analysis following it. And here we are showing that the exergy is having different components, exergy production, exergy destruction, and exergy losses, and the expression of the exergy is given here, which is the second equation. Then the exergy differences are being shown here.
Excuse me, doctor, what is difference between production and destruction?
Actually, it's somehow that's the production of the food. The way that this expression is written actually is not is not in its best shape. Actually, we used to put it as the exergies according with the flow in and flow out. That would make much difference, and then the exergy difference with the dead state. So what we mean here, basically, you can look at it as in terms of the energies or the exergies in and out of the system. That would probably be a better way to consider this. As you can see, it's written down there as in terms of in and out. Then looking at the exergetic efficiency for each one of the components, we'll find that the condenser is the problem. So if there's something that needs to be fixed, you better look at the condenser and fix it in terms of second law analysis first, and then look at the ejector. And probably I mentioned to you something about the ejectors earlier, that there are only small number of companies throughout the world that are working with ejectors. And the first law efficiency of the ejector is low. It's about 30% or low. Why is that? Because it has substantial entropy generation in the operation of the ejector and some sort of substantial amount of work in terms of thermodynamic analysis or in terms of patents that have been made or experimental work to come up with new configurations of the ejectors have been there, but still it needs further improvement to have higher performance to it. And you can see here that relatively speaking to the effect or comparison to the effect would say that it has a lower exergetic efficiency. After we did that, we said fine. So actually the work that I did not show all the work just because of the limitation of time and limitation of space. But the point is, you have seen the work done for 4 effects. If you go to visit the thesis of Khalid, which is, by the way, in the library website, you'll find that if you are going to do the analysis for a system of 6 effects, then the analysis would say, put your ejector after effect number 3. If it's 8 effect, put it after number 4. If it's 12 effects, put it after 6, and so on. So it's consistently showing that best performance for the ejector is when it's connected to the middle of the effect, middle of the system that we have. That was for a forward feed system. Then in a visit to my office, he was showing the results. I said, fine, we could see that for the forward feed. Let's have a look at it in the parallel feed and see how the performance is going to be. And he did the analysis for the parallel feed. What you see in front of you is a parallel feed MED system with flash boxes, but no preheaters. And the thermodynamic analysis has been done earlier, can be done for this unit, just to see the unit as operating as a parallel feed MED system, putting the energy balance equation for the parallel feed system. And because it's parallel, again, I need to remind you that for each one of the effects, there is sensible heating of the water which is being sprayed, and then latent heat. Sensible heat and then latent heat. The sensible heating here is going to be from TF to T1, And here it's going to be from TF to T2 and so on. So in every effect, there is a component of sensible heating and then a component of latent heat. This is what you see here. Sensible heating and then latent heat. Again, the L is nothing but the HFG. The first effect, again, steam which is coming into the HFG is, again, sensible heating and then latent heat. From the first effect to the second effect, this is the energy of condensation of the vapor leaving first effect and is going to be sprayed, is going to be condensed in the second effect. It's going to liberate this amount of energy. This amount of energy will need it first to sensibly heat the feed from TF to T2 and then generate some vapor. This vapor is going to go to effect number 3 and the story repeats itself. What is difference here in this expression is that we are accounting for vapor coming from the previous effect and the flash of vapor that leaves the flashing boxes to join it, which is basically this. Vapor is leaving effect number 2 is here, which is capital D2. And then there is DF2, which is formed by flashing. It's going to join this so that we have two components here that are going to enter into the next effect in the tube side. And this here, why you find that we have, this is the quantity that has formed by evaporation on top of the unit. And this is the quantity that has formed in the flash box. And both of them, again, are going to be sensible heating for the feed and then water heating. And for the condenser, we have, again, the vapor, which is leaving the last effect, plus the vapor, which is leaving the flash box of the last effect, associated with the last effect. So this is vapor formed, and this is the flashed of vapor, which both of them are going to preheat the feed and the cooling water from cooling water to TF. So this is for the unit without TVC, and then the TVC is going to be added again. And here this is just some sort of a validation of the work that has been done. And again, going back again to the addition of the TVC. So typically we'll start with the TVC that is linked to the last effect, seeing the performance. And then after that, we are going to shift from this into different locations of the TVC. So moving it from this location here to be connected to this, leaving third effect or second effect or first effect. Typically speaking, this is the kind of results that we could show. The interesting thing about this figure is that it is showing the effect of the number of effects on the performance of the system. We've seen figures like this previously with the forward feed, that the PR decreases slightly with increase of TS for every one of the cases, but the cases where the TVC is there is associated with higher performance ratio compared to the other units. So adding the TVC improves the performance ratio. And this improvement, again, I would remind you, this is because of the reduction in energy requirement from external source. We need less steam, which is the motive steam coming into the system that we have. Then similarly, what Khalid did is that he tried the value or the location of the TVC to change from the last effect to any of the other effects, and the same results could be shown, that we are going to have best results. If this is a four effect system, then basically the top here is the one for a TVC located after effect number 2, which is this. And the rest are slightly less than that. And the lowest required cooling water flow rate is associated with the condition where it is located in the middle. So this one you can see here. It is associated with the TVC after effect number 2. Specific heat transfer area was not really affected by the location of the TVC. And then he did again the second law analysis, showing which are the locations. Again, similarly, the condenser and the ejectors are the locations where with the lowest exergy efficiency here. Let's see what we have here in this figure. What we are trying to do here is that we're trying to see or analyze the case. If we are moving the TVC from one location to the other, what difference would it make? So we did that for effect of changing the location of the TVC on the performance ratio and the compression ratio for a system with 8 effects at 80 degrees centigrade top temperature. And this is what you could see. Look at this. This line is basically presenting the compression ratio. Let me see where my, so the line here, this one is representing the compression ratio, this dotted line here. What is the compression ratio? To remind you, it is pressure of the compressed steam leaving over pressure of the entrained vapor. So this is the compression ratio. When you are putting the TVC at lower stages, what happens at lower stages? You know, for an MED system, if I'm looking at the pressure into the number of stages, you'll find that it is decreasing. So it is continuously decreasing here. If you are going to keep the conditions going to the first effect at a constant pressure and temperature, and then you entrain from here or from here or from here, as you are going in this direction for n equal to 2 to 3 to 4, then you are going a declining pressure. So the compression ratio increases. The ratio between 1 and PS is known, or for example, PS over P1, if the TVC is located at 1. This is the compression ratio. But if it is located at 2, it will PS over P2. This is bigger because P2 is smaller. P3 is smaller, so the compression ratio is bigger. P4 is even smaller, so the compression ratio is bigger and bigger. So the compression ratio increases as you are moving the TVC away from the front. But the figure that we see here is the motive steam flow rate. The motive steam flow rate decreases as we are moving, as we are moving the TVC location. So we are having some sort of two counteracting parts. And if you are going to combine the effects together, we get this figure here, which is showing an optimum performance here at this location. So this location, which is showing the best location, is somewhere which is, if we are talking about 8 effects, so this is almost somewhere between 4 and 5, which is effect number 4. So after effect number 4 is the one which is showing higher PR for the system operation. So that was something in our trial just to see what's happening. Now we did that for a couple of temperatures. This one we did it for a maximum temperature of 80, steam temperature of 80, and this we did for a steam temperature of 70. Results are qualitatively the same. You are getting the highest PR performance ratio corresponding to having location of the TVC in the middle of the unit. Practically speaking, maybe I mentioned that earlier, that we were in a visit to one of our desalination systems in Marafiq, which is basically MED system. And we noticed that the system is made up of 8 effects. First 4 effects, and then a TVC, and then the last 4 effects. They call these the high pressure effects, and the low pressure effects, and the TVC is somewhere in the middle. So this has been a practice in the industry, And as usual, the industry keep these information secrets. They don't share it. That's why we could not find it reported in the open literature. And that's why we had to carry out this study. This is the effect of steam temperature on the performance ratio, or at more different motive steam condition. And we could see that there is again an optimum value of the motive steam where the system is better to be operated at. And when you notice here that the motive steam is not a small value, it's a big value. And there's a benefit from this. Because if you are going to extract steam from a low pressure turbine, then it will be steam of low pressure and temperature and high specific volume. High specific volume, it means that you need bigger pipes to drive the steam in. But at higher temperature or higher pressure, as you are seeing here, it's 1,500. At this condition, the value of the specific volume is less, which means that you can use smaller pipes. So this is also going to help us in having higher pressure, which means that it will higher temperature, it will not condense on the way of the pipe, and the pipe will be smaller in diameter. So it's another benefit that we are getting from operating this unit. I will not talk about the economic analysis today. We'll just keep a lecture talking about the economic analysis. We just have something like 4 minutes left for the class. So maybe we can dedicate half a class talking about the economic analysis. The point here that I would like probably to close with is that we have the new homework, which I'll try to make it available at the Blackboard just right after the class, is have something like 1, 2, 3, 4, 5 problems. The first 3 problems are for single effect evaporation. The first problem is single effect evaporation. Second is single effect evaporation with thermal vapor compression. The third is single effect evaporation with mechanical vapor compression. And then the fourth problem is about an MED system. And the fifth problem again with an MED system. So this is going to be problems making the next homework, and the due date is going to be 28th of March. And why the 28th of March? Because this is going to be, not the 28th. Actually, the 26th of March. I'm sorry. I think it will be like a Thursday. 26 is a Friday. So I'm not sure whether 26 or 25. The reason of making it like that is that our exam is going to be on the 27th, the midterm. So I just wanted to be submitted a couple of days before the midterm so that I can post the solution before the midterm for you to have a look at. So I'll just post it and you'll find the deadline I'm giving for the submission will be written on it there. So this is something that I wanted to share with you today. Next time, we're going to talk a little briefly about the multiple effect desalination system with mechanical vapor compression. And then after that, I'm going to show you different layouts that are possible, and some of them are actually available for MED systems that do exist. Yes, go ahead.
Assalamu alaikum, Doctor.
Alaikum assalam wa rahmatullah.
Thank you very much for the lecture, Doctor. I don't know whether I'm the only one involved. The homework 1 and homework 2. I don't know whether the grader is not of a desalination background or what. I don't know the reason why he savagely graded the homework. Basically, homework 1, homework 2. In homework 1, you ask us to reproduce a paper, which we spent a lot of time before we get a figure looking like what the author Haber did. And the second homework is on humidification and dehumidification. We also spent a lot of time, coupled with the fact that because I'm also new to EES, I'm just learning the EES. I spent a lot of time on both assignment or both homework. But with the way the grader get the homework, is either he doesn't have background in the dissemination system or he's new to grading homework. He suddenly removed my mark without any reason for, like, if I grade for other instructor, once I remove a student grade, I have to put the reason. So problem is in this analysis or sort. I don't understand.
So let's do something, Hamza. Yes, actually, this is why I posted the grades last night. And what I'm going to do is that I'm going to share the graded homeworks with you. And let me have your feedback on it on Wednesday. Just have a look at your papers. And this is the first time we get something out of the grader's hand. So let's just straighten it out by directing him if he did, if he was harsh in giving the marks, or if he took the marks without specific legitimate reason.
I think most of us facing the same problem.
Yes, actually.
Yes, I would expect that. I mean, since Hamzat has complained, so it will not only for him, it will be for everyone. So what I'm going to do is that I'm going to share it with you. I'll be emailing to every one of you his 2 homeworks. Have a look at them, and then let's discuss it on Wednesday so that we can send him a note of what things that should be done. Is that okay?
Okay. Thank you, Doctor.
Oh, you're welcome. Okay, just one thing before leaving, I forgot to mention that lately one of the students came to do his master with me, and what we wanted to do is some sort of structured way for looking at the location of the TVC. What we did and what I explained today was something like a parametric. Let's go for effect number 1, and then effect number 2, and then effect number 3, like sequentially moving the TVC from the front to the end. But we wanted to do something different, which is going through what we call a multi-objective optimization and seeing among the parameters that we would have, what would be the best location of the TVC. This work has been done, and actually, we are holding the thesis until we send the paper for publication. He finished his work, was it last April? Maybe last April or slightly before that, but that was some sort of a natural evolving of the development of the work with MED compared to what we have done earlier. So I'm going to stop here, and then I'll see you on Wednesday, inshallah. So again, a couple of things to be done. I'm going to release the next homework, and then I'm going to send you the homeworks, graded homeworks of the previous first and second ones, and then let's discuss it on Wednesday, as I mentioned, inshallah.
What about the recorded lecture and...
Oh yes, I'm sorry, I forgot to do that. I just get busy in other things, so I'll work on it also. I'll start today preparing it. Actually, it's for your course and for the other course, so I'll work on them and try to make them available as soon as I can.
Thank you.
Inshallah. You're welcome, sir. So see you on Wednesday, inshallah.
Assalamu alaikum, Doctor. Thank you.
Alaikum assalam wa rahmatullahi wa barakatuh.